Welcome everybody. We're going to start with today's session. Dr. Architect Christoph Krola is a licensed architect who combines his architectural practice laboratory for Explorative Architecture and Design Limited. With his position as turned as associated at the Chinese University of Hong Kong School of Architecture. After graduating from magna cum laude as a civil architectural engineer at Ghent University in 2003, he practiced in Belgium at Bureau Buildings and Techniques and independently designed and built his first project, House for an Artist. He moved to London in 2005 to attend the Architectural Association School of Architecture, London, Master of Architecture Program, Design Research Laboratory, from where his student work was exhibited in the year 2006 at Venice Architecture Biennale. Following this, he worked for several years as the lead architect for Pritzker Prize winning while teaching in parallel at the AA and other institutions worldwide. He is the founder of the International Workshop Series, which organize workshops worldwide, exploring digital design and fabrication in architecture, and has been invited as a jury critic, lecturer, and tutor in numerous institutions throughout Europe, North America, Asia, Australia, Chile, and South Africa. Dr. Christoph is currently based in Hong Kong, where he has practiced and received numerous design awards. He is best known for the projects Golden Moon and ZCB Bamboo Pavilion, for which he received the World's Architecture Festival for Small Projects of the year 2016 award. In 2018, he completed his PhD studies at RMIT Melbourne with the doctoral dissertation on building complexity, the more or less of post-digital architecture practice, for which he received the 2016 RMIT Vice Chancellor Prize for Research Impact, higher degree by research. In 2019, he was appointed by the International Work for Bamboo and Rattan as Task Force Expert member for bamboo construction. That's a lot of accomplishments, Doctor.
I've been busy.
Yes, you've been really busy. So I welcome you to this session. Dr. Christoph, the platform is all yours.
Okay, thank you so much, Ranjin. It's a pleasure to be here, and thank you so much for inviting me to join in this conference. I hope you've been having a good time in all the previous sessions that we've had. Let me start by sharing my screen. Are you seeing this?
Yes, we can see that.
Excellent. All right. So yes, the title of my talk for tonight is Building Complexity in Post-Digital Architecture Practice. As just mentioned, I'm Christoph Krola. I'm currently an associate professor at the University of Hong Kong. I've actually moved since the time that abstract was written that you just wrote. So as was just mentioned, I wear two hats. On the one hand, I'm a practitioner. So I have an office here in Hong Kong titled Laboratory for Explorative Architecture and Design. And in that office, I try to implement the gospel that I'm preaching in academics. So I'm an associate professor at the University of Hong Kong as well, where I teach at the Faculty of Architecture. But I'm also running a new program there titled Design Plus, which is a multidisciplinary design program that tries to apply design thinking in a much broader field than the typical silos in which you see architecture or design applied. So what I'll do today in the talk is I'll give you a short theoretical introduction framework to place the work, and then I'll use a series of projects to illustrate what I'll be talking about. So it'll be quite fun, quite relaxed. I've got several videos. It'll be quite graphic, so please enjoy the presentation. Questions, if it's urgent, you can stop me at any time if you want to. Otherwise, we can do the Q&A at the very end afterwards. I'm going to start with this quote by Bill Mitchell, who 15 years ago was saying that only projects of sufficient simplicity get designed and built. And now the question immediately becomes, what do you mean with simple? Well, it's the opposite of complex. And he defines complexity as the number of design decisions you need to make relative to the scale of a project. And in his article where he's elaborating on these terms, he breaks up the production of architecture into two parts. On the one hand, you have a design system. And on the other hand, you have a construction system. So the architects typically operate in the left column more than in the right column. And both of these parts have encoded aspects, which are basically the tools and the techniques that we're working with. And then the added design content, which is the added information that the people that realize architecture need to bring to the table on top of the tools that we're working with to realize our project. So for example, if we're talking about design systems, let's say that you want to design a curved wall. Up until a few decades ago, you would use these French curves to, for example, very precisely attempt to mark up which curved parts you would use. But then to translate that information to a contractor would be a very difficult and tedious process, which is why it's always been very difficult to just design curved architecture or curved designs in general. Well, nowadays, these types of French curves, these rulers that were part of the encoded aspects of the design system, they've been replaced with NURBS modeling geometry, where without even needing to know any of the complex mathematics behind it, anybody can just draw a few points on the screen and automatically a perfect NURBS geometry curve will be generated in between it by the methods and the mathematics that have been encoded in the design systems that we're working with. So you can imagine that the complexity of designing or drawing curves has dropped dramatically, and our ability to clearly communicate those has also dropped dramatically. So simplicity of construction is dependent on the tools and the techniques that we're working with. Now that's true not only for the design system, but also for the construction systems that we're working with. There too, you have encoded aspects and added construction content. For example, I'm from Belgium originally, where most of the architecture is made from bricks. If I would want to design a brick house in Belgium, I just need to give a few coordinates, and the craftsmen on site, with their years of expertise that they have, would easily be able to develop this brick project. If I would do that in Hong Kong, however, where there's no brick architecture, it's all steel and concrete, the encoded aspects are much weaker. There's less of a craft available locally, so the complexity would increase because I would need to add a lot of construction content to make sure that they can implement it. Now, throughout history, innovative architects have not only worked in the added design content sector where most commercial practice takes place, but they've been addressing the encoded aspects as well, and both of the design and the construction system. Just to give you an example, Brunelleschi's Dome of Firenze from 1436 won the competition to span the cathedral because he not only designed a very elegant shape, but he also figured out a new method of bricklaying that allowed him to build this dome without needing a scaffolding, which would have been expensive to reach the very top. So he tackled both the encoded aspects of the construction system and then the added construction content, added design content, and encoded aspects of the design system to arrive at this innovative solution over 500 years ago. Now, similarly, a few years back, for example, Zaha Hadid Architects designed and built the Dongdaemun Plaza in Seoul, which is a project that has over 45,000 differently shaped, unique facade panels to define its envelope. And that would not have been possible without the multi-piston pneumatic press that's parametrically controllable that you see on top of it there. So again, they attacked the problem by tapping both into the encoded aspects of the construction system and of course also the design systems where they were writing their own codes to make this possible. So my claim is that innovative architectural design is more likely to happen if you tackle both encoded aspects and the added content to it, or at least there's a greater opportunity for innovation if you also challenge the tools that we're working with. Where there's something very unique happening at this day and age, like the current generation of architects, is that because of computational technological evolution, we now have computational control of these encoded aspects, which dramatically open the design solution space that we have at our disposal. So my work focuses on addressing innovation in architecture by tackling the encoded aspects and the added content in both the design and the construction systems. Now, there's a few things that you should know to illustrate how paradigm shifting today's age can be. The first one is your washing machine at home has more computing power in it than NASA used to put a man on the moon. That's a fact. They don't make slow processors anymore the way they did it back in the 60s. So computational power has become a resource that is available in abundance. It's everywhere to such a degree that we're even using it to do our laundry. So that's something that we can really tap into. Nicolas Negroponte, the founder of the Media Lab, said in '98 already that we should face it, the digital revolution is over. like air and drinking water, being digital will be noticed only by its absence, not its presence. And that's very true if you see how we communicate in this day and age. For example, here through this Zoom presentation, the digital technology is embedded in the system. We don't even see it. It's just there, and it allows for a radical change in how we communicate. In the construction industry, however, it's very often still lacking, or at least we haven't fully maximized the opportunities that we have at our disposal. Another fact, our Apple AirPods that you may have bought recently, they have more computer power inside of them than an iPhone 3 did only 9 years ago. So you can see that the power of computation still continues to shrink in size, shrink in cost, increase in power. So that's a curve that keeps on accelerating, and that's going to continue to change our environment for generations to come. However, Bill Gibson, the future's already here. It's just not evenly distributed. It's not because here in our university lab, for example, we have access to robots that we'll be able to build with robots if we're operating in rural China, for example. So as architects interested in practicing, we have to be aware of the uneven distributions in technology that we have, and ideally tap into them in a productive manner to realize our works. I found this example from India from a few years back, where they were selling smartphones for under $4 US. Apparently it turned out to be a scam in the end, but the message is still clear that smartphone technology is now successfully bringing computation to anybody's fingertips, wherever you go on the globe. There are articles written about how, for example, access to the world web through smartphones is dramatically changing how business can be done from a slum in Mumbai, for example, where people can produce their goods and directly place them on a global market. The question is, though, how can architecture also similarly be disrupted by this technology? So that's kind of the theoretical framework that I'm operating in. So on the largest scale, I would say that we're working in a post-digital architectural era, where the main aim is no longer to just develop the next cool, funky tool or the great graphic on our screen, but to really see how we can use all of this technology and bring it back into the physical world of praxis, only this time informed by decades of working with computers. Now, under this post-digital field, there's many subcategories, and the field that interests me most underneath that is what I've titled as building simplexity, by which I mean work trying to overcome the construction complexities that are often associated with digital non-standard designs through the simplest of means, using digital design tools as a weapon of choice to root the work back in a human-centered construction reality. That will become very clear from the presentation I'll give you later. Our aim is to benefit and maintain, hold on to and maintain the unique qualities that non-standard architecture can bring, which can easily be simulated digitally, but make that possible without per se increasing cost, increasing wastefulness, and decreasing sustainability. And the approach for this type of work centers on the incorporation of form, matter, material systems, and materializations as design drivers from the conceptual design stage onwards. And often that requires an incorporation of slippage and on-site serendipity and variability as productive drivers of the design solutions that we're seeking for. So that's kind of the theoretical framework. I'll show you roughly 6 projects, which are the ones that are listed here. And my aim is to basically show you how through those contemporary practice can dab into the fields of applied computational design, machine learning, and CNC technology integration in all of its forms in a productive manner. So just to set the tone, I want to start with an art installation that we did a few years back here in Hong Kong for a coffee brand that I'm not going to name. It's just a standard, it's a non-standard art piece that we were asked to produce, and it's basically a kinetic structure. It's a sculpture that is hanging over the coffee space. And in the next video, you'll see what our intention was. The intention was to create a surface that very, very slowly moves over a 2-hour cycle period, so slow that if you see it from underneath it, you don't really know that it's moving. But occasionally it will pop and shiver and move a little bit. And the story behind it was that if people take their time to enjoy their coffee, only then will they notice the slow changes that take place around them in a busy environment. as Hong Kong. And why I'm starting with this one is to illustrate that affect and spatial experience and emotional response to materiality is something that's central through our work. And throughout the talk, you'll see that I'll go from more affective, very emotional work to something that's much more rational and grounded. So please enjoy the first video. So that project was just to set the tone. Let me now start with the first big project, which was Golden Moon, which we built in Victoria Park 9 years ago for the Mid-Autumn Festival, which here in Hong Kong was just yesterday. So it's quite a timely project. And it's basically a large lantern installation that we built. Now, the Mid-Autumn Festival is a very important festival in Hong Kong. It's so important that it's even on our dollar bills. And it's basically a lantern festival. It's when families come together with their children, and it's a night festival, and people go outside with the lanterns to enjoy festivities. Like originally, it was meant to be a harvest festival where people would celebrate the end of the harvest. And in Hong Kong, a few years back, they organized a competition to design a lantern wonderland as part of this event in Victoria Park here in Hong Kong. Now, while we were designing, we heard this story, which is the legend of Mid-Autumn Festival, which is quite a fascinating story. Thousands and thousands of years ago, there was a Chinese archer, Hou Yi, who saved planet Earth from burning because 10 suns were circling the planet, and he shot down 9 of the 10 suns. And as a payment, which is why there's only one sun nowadays, and as a payment for saving planet Earth, the gods gave him this immortality pill, but the pill was not yet ripe. He needed to keep it for 1 year and then take it, and he would become an immortal god. So he hid the pill in his night cabinet next to his bed, and his wife, Shang'e, or Sang'o, when she found the pill while cleaning the house, she did what every household wife would do with random pills. She just took them. And unfortunately, when you take an unripe immortality pill, legend has it that you start to float. So she started to float, and the winds took her, and they drifted her off all the way to the moon. And Hou Yi tried to catch her, but he failed. And that's why the moon goddess, Shang'e, has since then been stuck on the moon. And only once a year is her husband, Hou Yi, allowed to go and visit her on the moon. So that's the real story of the legend of the Mid-Autumn Festival and Shang'e, the moon goddess. So we thought that was a funny story, and we thought that we would enter the competition with a design called Burning Moon, which is basically this flaming fireball. The idea being that if a young and beautiful couple sees each other only once per year, just from the heat and the passion and the friction alone, it gets so hot that the moon catches fire. So we entered with a design called Burning Moon, which was a practical joke. We didn't really expect to win, but we decided from the very beginning to design the proposal using the same materials that people always use to make lanterns, which is just bamboo, an LED light, a bit of fabric. And with this detail, we decided to populate this dome that would basically be the moon brought into Hong Kong. and we entered with the title Burning Moon, as I just said. So here you see the installation and the renders that we submitted for the competition. People would be able to go inside of it, where there would be all kinds of lanterns hanging, because the competition brief required a lantern of lanterns. And these are the actual competition documents that we submitted. So we said to build this, it's very easy. You just build a steel geodesic dome, you clad it with bamboo, then you put that component on it that I just sketched, and voila, you have the Burning Moon installation. To our surprise, a few weeks after that, the client called us back and said, congratulations, you won. But under two conditions. First, burning in Chinese cultures has nothing to do with love or passion. Burning means destruction or sacrificing something to the gods. And there's no way that on the Moon Festival we're going to destroy the moon or sacrifice it to the gods. So we have to change the name. It has to become Golden Moon. We said our joke doesn't work anymore, but whatever. The client said nobody got the joke anyway, so we agreed. And then the second requirement was that we had to stick to this schedule, which was that from the drawings that I just showed you, we had 3 weeks time to develop a tender package, and then the government would organize a tender, and only 3 weeks before we would go on site, we know who was going to be building that. And then we would only have 11 days on site, 1 day for testing, 6 days of festival, and then 2 days of demolition, and that was it. And we're talking about a 6-story tall, complex, non-standard structure. The design didn't change much. We shrank the pool down a little bit, but in principle, it remained this pathway in the reflection pool that would take people inside this large dome structure, where they would basically be able to see this complex light show and spectacle around them. And we were not allowed to make any foundations, so the structure was a simple steel base weighed down with a concrete slab, on top of which a steel geodesic dome would be placed that would be clad with 2 kilometers of bamboo to create a double curved diagrid. That would form the basis for 477 fabric flames that would be placed on top of this diagrid. Now, typically, if you were to design a dome, you would follow Buckminster Fuller's Bucky dome principle, which is this idea that you break your dome down into repetitive patches that can easily be fabricated with exactly the same geometries. Now, the downside of that is that you arrive at a hermetically sealed geometry that you really need to break in order to get into. It's efficient, but it's much more static, and it doesn't have as much punch as other geometries might have. So we looked around, and we found this formula from Fibonacci, that a scientist from the Renaissance, that basically allows you to project geometry onto a sphere in such a way that you get quasi-repetition around the equator and still some orientation and originality around the poles. And basically that's the same pattern that you find in nature when you're looking at a sunflower, for example. So we took that mathematical concept and applied it on our dome structure, tilted the sphere on an axis, and that produced this kind of oculus that you have on the inside, where you can still see the sky behind it. Now, to build this was a challenge, and the first thing we did in typical BIM strategy is to identify all the members that we're working with. And the way we planned to build this was to break it down into several steps, where first we would build the steel structure, and then on the steel structure we would apply markings that would allow us to identify exactly where a second layer of bamboo would go over it. So markings on the steel structures with matching markings on the bamboo would allow us to span these big triangles that you see here. And then on this first layer of bamboo, there would be other markings as well that would allow us to map a second layer of bamboo on top of it. So that way we'd be able to build it without needing any drawings on site. The steel structure was straightforward. We went to, the contractor took us to Guangzhou, where there was this shipyard where every year they built around 20 200-meter long container ships by hand, pretty much, with very primitive tools from big steel sheets. And these are the construction drawings that we produced for that. So our steel structure is a geodesic dome. There's only a few types of members, all with a constant radius that are required. We numbered all of them. So this, for example, member S5 that runs from the members S1, 2, 3, 4 to the members S9, 10, 29, 31, and 33 here. And on those, we would have markings where the bamboo members would need to intersect them. So these drawings were given to the manufacturer. And the way they were built is in a very simple way. It's similar to how oil pipelines are being built. So what you see here is an induction coil, basically a glorified microwave with which you heat up the steel pipes that are pushed through it. And then with these rollers that are manually controlled, they basically rolled all the pipes into their correct diameter. Now, when I asked how precise this was going to be, I was really shocked in the factory to find these guys. So I don't know if you see what's happening in the picture here. So what they did is they made a mold on the ground of the perfect circle radius that we needed to have for our structure. And this is a bucket of ice water. This is a fan, and this is a blowtorch. And what these guys are doing is manually heating and cooling down these massive steel pipes to manually bend them until they fit in the mold that is required. And that kind of freaked me out because if the steel structure wouldn't fit, the whole project would not be possible. So when I asked the fabricator, can we please test assemble this before we go on site? Otherwise we're in trouble. They said there's no time. We'll have to do it for the first time on site. But luckily they followed our instructions nicely. Everything was nicely labeled as we had required. Everything was marked up. So once the steel pipes arrived on site, to my surprise, in a very short amount of time, basically in 3 days, they managed to assemble this whole steel structure. This is us and a cherry picker trying to make sure that none of the members are swapped. But the simple logical approach made it possible to assemble this relatively easily. Then, as I mentioned, we needed to map 2 kilometers of bamboo over this diagrid. And these are the construction drawings that we produced for that. So this is, for example, member 29 that would be built up of maybe 3 pieces. We didn't know how long the bamboo was going to be. And this is where we need to intersect with the steel structure. And the red would be where the next bamboo layer would go on top of it. And with Sharpies, very simple and simple rulers, in no time, the bamboo is marked up. And here you see them installing everything on site. So the grid that you see is temporary scaffolding, and the diagonal lines are the big members of the diagrid that are being bent over the steel structure by these guys here. So these are bamboo scaffolders. All of them, they're real Spider-Man. They wear safety harnesses, but they don't hook them up to anything. They're just using these plastic ties to tie the bamboo together. And here you see them on top trying to figure out the geometry at the very tip. Just following a very simple script applied in action. Then on top of that, the challenge was to put the fabric flames. Now, unfortunately, the Fibonacci sequence produces unique geometries for each and every flame. So the way we resolved that was by clustering these 477 geometries that we had into 10 groups of the most common denominators. And we could do that because we knew the fabric was elastic, the hinges were elastic, so there was a bit of flex available in the system that we had designed. So in the end, we snapped all the geometries down into 10 types with dimensions ranging between boundaries. So not with fixed dimensions, but with dimensions ranging between boundaries. And you can see that we actually managed to create quite a bit of repetition for some of the types around the equator, and then some more unique pieces around the poles. And this was done with a very simple algorithm principle called k-means clustering, which is a form of machine learning. So just to explain what the principle there is, if you have a data set that is multidimensional, doesn't have to be 2-dimensional like this one, and you want to group it according to its most common denominators, then one way to do that is by randomly placing as many points as you want to have groups. So in this case, let's say you want to have 3 clusters. And then what you do is you try to identify which points are closest to these centers. Then you define the geometry, or actually the group that sits with each cluster, and you try to find the average of that group. And then you move your center point to the average, and you run that again and again. So you find the points that are closest to it, you average them out. You move your center point, you find the points that are closest, and you average them out. And if you run that several times, eventually you'll arrive at a stable setup. So it's a looping script that you can just generate. It doesn't always arrive at exactly the same setup, but it arrives at a clustering principle that works very well. And you can do this for any number of seeds in any type number of dimensions with any number of populations. So here you see an example of 500 seeds with 15 clusters, and you see the system still kind of finds its solution very easily. So here you see it running again. So with that principle, we managed to snap our two-dimensional geometry or multi-dimensional geometry here into some common groups. Now, unfortunately, the client told us that we couldn't do this with white fabric because white lanterns in Chinese cultures are only for funerals. So they forced us to add a layer of color on top of this. But here you see in this matrix that we still had a very strong rationalization of our geometry. Rather than producing 477 different flames, yeah, we still had a strong repetition here. And then once we had that, all we had to do is figure out the details on how to connect things. Here you see us very quickly cutting the fabric to a correct size and on site using bamboo and plastic electrical tubing to make hinges. We made these simple flames that could be placed over the bamboo diagrids and fixed with just metal wire and zip ties in a very short amount of time. So you see that in under 15 minutes per flame, they were able to populate the geometry with the flames. Now, while this was going up, we were using these LED light dot strings that in Hong Kong they use to decorate their facades around Christmas or Chinese New Year, the facades of the high rises. So we recycled that technology and made basically a 1 megapixel spherical screen on top of the dome that allowed us to run videos over it. And then here you see the day before the opening, when the pavilion kind of had a bad hair day still. Now, digitally, it's very easy to very precisely identify exactly where each flame tip needed to be. But it's impractical to demand that in a quick and fast construction site like what we had here. So instead, what did we do? We came up with a system where we'd have metal wires running from the top of the sphere all the way down to connect all the tips of flames that were part of one of the same strips. And what we would do is we would be shouting from the ground to this guy here, that flame needs to be a little bit more, a little bit less. Now we did that for 1 in say 10, 15 flames, something like that. And once we roughly had the haircut direction kind of fixed, and we told the craftsman, now just follow the flow, have all the other flames kind of follow the system, which is much more practical and time effective to implement. Here you see it the morning of the opening, taking down the scaffolding. This is 3 hours before the opening where you see the strong coloration. An hour before opening, but this was really a nighttime festival, so this is how it's supposed to be perceived. So you see that the strong color contrast is totally smooth now. And what's really interesting is that this is the very precise, mathematically correct computer drawing that we submitted in the competition, and this is the final as-built form. And you'll see that these imperfections and these unpredictabilities that kind of crept into the project gave it much more personality, gave it a lot more punch. So it became a much more charismatic and sympathetic pavilion in the end. So here you see the entrance. As we're going in, you get a sense of scale of how big this is. So one of these flames is around 4.5 meters, something like that. As people would go in, here you see the messy data boxes around the equator to send the signals out to the videos. And this was the competition entry image, and this is the final as-built image. Now, this looks like a static image, but in reality, the lanterns were swaying in the wind. The pattern is swooping to that black oculus on top, and colors are constantly changing because of the animations that were running onto the installation. So as you entered, you kind of lost all typical reference to that you used to define your space. So it was a very unique, otherworldly experience to be part of this event space, to the extent that we had to triple the queuing area and usher people out with staff because people were just getting hypnotized inside. So we had over 400,000 people seeing this in the 6 days that it was up. Here you see the colors that it can take because of the LED lights. And here you have a view of what it looks like from the tens of thousands of apartments looking down on Victoria Park. There's some nice videos online on our website. I'll show you the link at the end of the talk that you can have a look at later. But yeah, I have to thank Lee Kum Kee Soy Sauce for sponsoring this. This was a very fun project a few years back. The year after that, a friend of mine from China in Changsha sent me this photo. I don't know who did this. I don't know how many of them there were made, but somebody somewhere in the middle of a highway in Changsha for the following year's Mid-Autumn Festival made an inflatable copy of our project, which I think is fantastic. I think it's very clever. I'd love to know who's behind this one. Now that project 3 years later led me to build the ZCB Bamboo Pavilion here in Hong Kong, and also maybe a little bit more of a specialist in bamboo. To this day, I would not call myself a bamboo specialist yet, but I'm an architect who can kind of work with this material, because the bamboo world is vast. There's over 1,200 species, and botanists have way more knowledge of the plant. I just know enough about it to be able to design with it. And I do think bamboo is an incredibly important material, because if you look at where it grows across the world, and if you overlay on top of this map the 12 largest cities by 2030, or the 12 areas of highest urban growth, then you'll see that bamboo is available in those parts of the world. So if we would be able to embed bamboo in our everyday construction, we would be able to contribute to the reduction of the carbon footprint of the construction industry. Reasons for that being that bamboo is far more sustainable than any other construction material, much more sustainable than wood, because it grows much faster. It can grow up to 1 meter a day, and it can be harvested in 3 to 5 year cycles, meaning that it's much more productive than sustainable wood plantation would be. Unfortunately, because it wasn't present in Western Europe or in big parts of the US during the times when building codes were written that are now adopted across the whole world, bamboo never really made it into the modern architectural construction world. It's always been a poor man's construction material. Now in Hong Kong, however, bamboo has been around forever as a temporary support material. So all the high rises that you'll find in Hong Kong are built with bamboo scaffolding. Also, all the support structures that you see, if you want to fix something on the street, they'll use bamboo and hook it up to drain pipes and bicycle racks and handrails to make these spectacular structures. Every year, over 5 million bamboo poles are brought into Hong Kong and used in the construction industry, and discarded afterwards as well, because they're not being treated. And the way these bamboo craftsmen here in Hong Kong work is they use rules of thumb like leg lengths and shoulder heights to define these grids, and some simple knots that I can teach you in 15 minutes to make these amazing structures. Now, what's really nice about Hong Kong is that for the religious festivals like Cantonese opera, every year when there's no COVID, typically over 40 of these temporary bamboo structures are being built as well to house Cantonese opera events. And these are very, very nice structures using very simple grid systems that are hoisted and assembled on site. And a few years back, when William Lim, one of our most celebrated architects, was asked to design the biggest bamboo theater Hong Kong had ever seen, all he could really do was scale up this typology to the point when the bamboo material would start to fail, and they would start to replace the bamboo with tree trunks to make these big, large theaters. So a few years back, when we were asked by the government to build a bamboo cover of this square here in front of the ZCB building, the Zero Carbon building, with a brief to host public events, showcase bamboo potential and promote sustainability, we thought this was a great opportunity to challenge what event spaces could be built with bamboo. And we did this by tapping into a very unique property of bamboo. So bamboo, as you know, probably is a hollow column with diaphragms to separate these nodes. And these diaphragms make bamboo incredibly good at bending because they prevent the buckling of the hollow pipe if you would bend it. Now, this bending property of geometry is something that with digital tools, we can very easily simulate. So we can very easily give a behavior to a curve where we can predict how it would straighten itself out, or how it would bend if you would bring points close to each other, or how a network of curves would behave. With free available tools online like Kangaroo and Grasshopper, this is possible. The challenge, however, of working with bamboo was that bamboo is a natural material. Every column is different. Like here you see all bamboo, a series of bamboo columns that were used in our ZCB Bamboo Pavilion. All of these have exactly the same specification. Now imagine if you do a steel structure and all your steel members with the same specification come in with the same geometry deviation. It will be impossible to build. So our concepts of precision and tolerance need to be totally changed if we're working with a natural material. And still, we were able to make an event space to scale that looks radically different from the typologies that typical Cantonese bamboo craftsmanship can produce. So how did we manage to do that? Well, we started off with a design competition where I hired 20 students and split them into separate groups. And the brief was use split bamboos to come up with a concept of how the tectonic system would work and do this in an iterative fashion. Make a model, identify the problems, and improve it. And one of the teams came up with these 5 models where they started off with a tripod, which is per definition stable. Then they figured out there is a weakness here, so they brought these wrists down to the ground. They started to discern a pattern on top, so they cleaned up the pattern. Then they still saw a weakness at the hinge here. So they thought, what if we curve this? Or what if we turn this into a circle that folds onto itself? That's how they arrived at this concept model. Then my team took this on, and we turned it into a digital model where we brought all the site parameters in, and through a lot of trial and error, we identified the input topology of our physics simulation engine, the lines that we gave a behavior similar to Bamboo that tries to straighten itself out, and then identified the forces that we would need to apply to those topologies to bend the geometry so that it would wrap around these fixed circular foundations. So we didn't draw these final curves. We draw geometry, gave it a behavior, and pressed play. And the geometry kind of emerged from the digital simulation engines that we had set up. And with that, we arrived at this bamboo pavilion spanning 37 meters, which to my knowledge is still the largest bending active bamboo shell built today, hopefully not for long. And it became this beautiful structure. How did we build this one? So we worked with Mao Tsuk, which is a giant timber bamboo species that grows close to Hong Kong across the border. Different parts of the world have different species. India has a different timber species as well that can be used. But these are rather thick columns, and they grow in the Guangdong province. And they're harvested with very primitive means from these bamboo plantations, centralized into a central collection point. And the first thing that we need to do if you work with bamboo is to treat it. Bamboo can be permanent if you design it so that it is not wet, so you prevent it from water, you prevent it from UV light, so you don't expose it to the sun, because it will disintegrate it over time as well. And you also have to treat it for biotic attack, bugs and mold and fungus and stuff like that. And to treat it, there's many ways. A cheap and environmentally sustainable way is to submerge it in a borax and boric acid solution, which is just a salt solution, a natural salt solution. So you make these big containers, you perforate the bamboo so that the liquid can go inside, and then those you submerge in a salt solution for 24 hours, and basically the sugar inside the bamboo is washed out, and you end up with a bamboo that can be permanent. Now, while we were treating the bamboo, we were preparing the foundations on site. And just to illustrate why these foundations were important, you've probably all seen these Volvo Ocean races on TV. Now, one of these boats weighs around 12.5 tons and has a downwind sail area of 578 square meters. It's quite large. Now, our structure weighs around half the weight and has almost twice the sail area, and we need to withstand typhoon forces. So the foundations were essential in holding the pavilion down. So now, the way the load path works is that wind blows on the fabric transfers the load to the bamboo. So the fabric needs to be very tight. And then the bamboo transfers the load down to the foundation. And that connection is absolutely crucial because you need to prevent lift. And the way we did that is we borrowed the detail from a Colombian bamboo architect, Simon Velez, and basically cast a rebar into the concrete, from the concrete into the bamboo, using the interior profile of the bamboo and non-shrink grout to prevent the bamboo from sliding off the rebar. So how is that done? Standard foundation, rebar sticking out, and here you see us just manually with a steel pipe and some 3D, triangles printed with a simple A3 printer until we're roughly where we need it to be. So here you see the rebars waiting. And then the little sockles at the base to prevent the bamboo from getting wet were just made with a PVC pipe that was cut to the correct angle that we extracted from our digital models. And in a very cheap and effective way, we managed to make these beautiful little sockles to hold the bamboo at the base. Then the bamboo arrived to site. Everything was nicely cleaned, protected from the sun. And the next challenge was, how do we translate this three-dimensional model, which is basically a data cloud, into something that can be built on site by people that don't speak English, but also don't read plans typically. So what we did is similar to the Golden Moon. We identified the line work and where they would intersect, and we unrolled all the curves digitally and we kept track of where one member is supposed to intersect with another member. So here you see the only construction drawings that we gave to the people on site. And we gave these, so these are drawings that show where member A15, which is built up of all of these separate poles, intersect with other members at which distances. Now we printed this sticker sheet, which is, for example, here is sticker C14 applied on the point on pole C14 where it intersects with pole A2, B14, and C14. So what the contractors had to do was just read our spreadsheets, get the bamboo pole, cut it to the right size, number it, and then we made this 40-meter long bamboo table in which they would put all the members together. And using metal wire this time, we would tie all the bamboo columns together into these 80-meter long or 60-meter long interconnected bamboo twigs. And then using a simple ruler, a Sharpie again, and a sticker, they would mark up where that pole is supposed to intersect with the other directions. And then, after we build a temporary scaffolding on site first, they could basically hoist these interconnected bamboo sticks onto the site, on top of the structure, and slide it over the correct rebar. And then for the first 10, 15 poles, we did project some of the coordinates down to the ground. But basically the idea was that the more poles you have up there, the more intersection points you have to correctly place the next layer. So without any heat bending, no added energy, just cold manpower, the bamboo comes bent over the structure itself on site, and then using simple tools like these wedges, the craftsman on site would try to match the sticker labels as close as possible and basically tie the structure together by hand. So this is what a point in our 3D model becomes. So you see it's like a cloud of approximation. It's not super precise, but it's the only way that a natural material would be able to find its solution. So here you see the structure finished. Now once we're done with that, we had to connect it to the foundation. And for that, we first centered the bamboo poles to the rebar, just drilled a hole at the bottom of them, and then sealed off the base, and then used the old fire hose that we cut up to just manually squeeze the cement into the bamboo poles until they were totally full, which you could hear by tapping on the side of the column, creating this very simple, nice detail that with a metal spanner was locked in place. So here you see the complexity of the geometry being built very simply with primitive tools. So then this is a structure when it was completed. Then the challenge was to put the membrane on top of it. And as I mentioned, this needed to be a tailor-made suit. Otherwise, if the fabric would flap in the wind, it would just tear apart under a typhoon. So for that, what we did is we measured all the triangles by hand on site. And I realized that everybody on site had a smartphone in their pocket anyway. So we set up the shared Google Doc in which everybody just punched the correct numbers while they were measuring. And with that data, we could automatically reverse engineer the triangulated cutting pattern that would be necessary later on. We could make models of that to test if it was correct. A cutting pattern that we could then bring to a fabric factory, which is this one here in Shenzhen, where they had a 15-meter long cutting table onto which they could basically have this little wheel cutting the triangle fabrics with super high accuracy. So here you see them unrolling the fabric, and then the cutter would whiz across to connect to cut these perfect triangles. These guys here are manually sticking a little strip on matching edges to connect them. And then these two men are fusing, welding the fabric together to create this one giant sleeve that was basically draped over the bamboo structure to perfection. So here you see the tailor-made suit fitting nicely on top of the structure, and here being tied on the inside. Everything was tensioned up, the details were fixed, and the scaffolding was removed. And here you see how light, how thin the structure is underneath it, and how large the span is. So simple details were fixed and finished off afterwards. And that's the final structure. So from an architectural design perspective, the aim behind this was to create a shield of the corporate architecture that was around it, to create this pavilion that would bring the focus back to the events that would take place underneath it, and also to the green park around it, rather than to the corporate architecture higher up. So here you see people enjoying the opening event where all the models are in place. Here you see from a bottom perspective the simplicity of the topology, so a triangulated grid that folds down onto itself. And yeah, this is how the structure basically allowed the design solution space of Cantonese bamboo craftsmanship to expand into an entirely different type of architecture without changing the craft much, just changing strategic aspects of the encoded design tools and the encoded construction tools. Now, this project got a lot of great attention, of course, which is always nice, but Hong Kong doesn't need anything like that. So since then, my team and I have been pushing hard to find applications in areas of the world that are more needed. So this is an example of something that we designed in Myanmar, in Yangon, where there's this pipeline that cuts through the heart of, all the way down to the heart of town. And on both sides of the pipeline, informal urban farming is taking place. And here on the right side, there's a little school that also was in need of a playground. So what we decided to do is to design this marketplace / playground on the pipeline that these local communities could build themselves with our help, of course, for relatively low cost, a very nice and dramatic space. Now, unfortunately, this project didn't go ahead, but we're right now pushing with Blue Temple, which is a local architecture practice that we're working with, to push for this shell, which is, so that all the groundworks have already been done, which would be a nice bamboo cover of playground in a park somewhere there. So hopefully in the coming years, we'll be able to see this one built. This is a quick art project that pushes the bamboo work in another direction. So just again to show a different simple logical system, originally developed by Frei Otto, who you may know, a famous engineer from the second half of the 20th century, Pritzker Prize winner in 2015. And he came up with this system called a bending active grid shell structure. So if you make a grid with no shear rigidity in its joints, but that is equidistant, then that's a very easily buildable grid. And that can easily be deformed, as you can see here. So this is an easy thing to make and just a twist. Now, this same simple system, if you squeeze this through a ring, then these types of geometries are also possible with it. And if you trim off the base, you basically end up with a double curved shell that has a very easy construction principle behind it. And he used that back in the 70s to build the Mannheim Multihalle, which is a very large, doubly curved wooden grid shell structure with a complex geometry, as you can see here. And now back in the day, they defined these topologies with very, very elaborate physical models like the one that you see here, very time consuming to make. But with our tools nowadays, we can simulate this in a matter of seconds. And this simple concept of an equidistant grid was built from wooden slats, all same dimension, simple joint, and then pushed up by these pressing points, as you see here, to basically create the final pop-up grid shell that you see here. Now, with my students, we tested if this would also be possible with bamboo, and we built this little grid shell here on the rooftop at CUHK a few years back in only 2 or 3 days' time from very, very thin bamboo sticks. And the double curved geometry basically creates a very strong shell. You can even hang from it. So that's cool, that's exciting, but it's a very dry bubble geometry. So with my team, we started thinking, how can we push that geometry again into a different, more engaging environment? And we found out that if you take an equidistant grid like this one here, and inside all your squares, you add a few pentagons as a singularity, then you can actually make columns inside your bubble. And these can still be distorted as well. So you can arrive at a very different design solution space that doesn't per se make the construction much more difficult. And we tested this, for example, in an aluminum structure that you see here that we did for the Design Society in Shenzhen a few years back, entirely made from aluminum tent poles that you just use for your normal camping tent, all with components that we just bought of Taobao for next to nothing. So the concepts apply to different materials as well. Anyway, with that principle in mind, we were invited to do an art installation in Taiwan 2 years back now, before COVID, and this is the video of that. A smaller Bamboo project after that is pushing the construction technology, embedded construction technology to a next level. So here we're starting to see how augmented reality can continue to expand what we can actually do on site. So I don't know if you've ever had one of those on your head. So this is a HoloLens by Microsoft, and it's basically a pair of glasses that are see-through, but with a screen in between, allowing you to project holographic content on top of your hands. And holographic technology, it's been around for a few years. It's also in a lot of our smartphones already. You may have seen applications of that as well. So it's something that many of us carry in our pockets already. So we thought it'd be interesting to see if we could create a collaborative artwork with 30 students working from the same model over 3-4 days to build an art piece without knowing what the architecture eventually would be. And as a challenge, we made the most complex shape that we could possibly think of to be built with bamboo splits. And now the way we built that was by using these HoloLenses, this time to not use rulers or markers, but direct holographic instruction overlaid onto the hands of the people to mark up bamboo splits and then bring those together. Using these, again, holographic guides that would be virtually available, but not in reality, only visible to the people that would either look at them through their phones or through the HoloLens. So this is what somebody would see if they would look through the lenses, or this diagram. So this is a very, very fun, quick project that we did with a group of students that could dramatically open up the complexities of what we can build on site. And this is the video for that.
You got an organ going there. No wonder the sound has so much body.
So that's fun. So with that technology, we're now starting to see and plan ahead, hopefully once COVID is over, to see if we can actually build a maybe more complex structure like this one. And a few months ago, we did a trial already, which you can see here, of one of the legs, where the students were actually using, again, these holographic instructions to mark up and then later on also assemble. Yeah, video's jittery a bit. Assemble basically components of this, and these holographic guides become the drivers of the assembly process. And in a relatively short amount of time, they were able to build this one leg of the structure, which is strong enough again to hold somebody hanging from it. What's really interesting though is that these lenses embedded in them have cameras as well, that allow you to, if you place these little QR codes onto the structure itself, to track in real time what the as-built is that you have created. So that opens up all kinds of opportunities for real-time feedback of the structural performance, for example, of what your as-built would generate. So here you see the lady going around, and on the screen in the back, you see what it is that she's looking at, and the computer automatically recreating the as-built model. So that's fun. That's some of the latest work that we're working on here. To wrap up the talk, I want to show you that the concept that I'm talking about here is also applicable to all kinds of different materials. It doesn't have to be bamboo at all. So this is a project that we did last year that got some nice attention as well. It's a mountain retreat in Hokkaido, Japan, that hasn't been built, so it's a concept for it. And the idea behind it is very simple. It's very performance driven. If you take a beam and you span a certain area with it, then you need a certain amount of material to withstand the fixed load. Now, that material is not optimally used because you have a neutral fiber in the middle. And basically, the structure collapses if only in one part the material reaches its maximum stress. Now you can optimize this further by, for example, changing the shape of the geometry. But if you would set up an evolutionary algorithm to find out what geometry would be the very best to withstand a certain load for the least amount of material, you'll automatically end up with a chain line or a catenary, which is under pure tension everywhere. And you just saw that the weight reduction requirement can go up to 90%. So there's a huge material saving possible there. This is not something that we invented. The Yoyogi National Stadium by Kenzo Tange that you may have seen in the Olympics a few weeks back applies this principle using steel roof profiles to define the geometries of its main hall, or the very, very nice geometry of the smaller hall next to it. So it's a very nice, elegant system. Back in the late 80s, Fraiotto again applied this principle for glue lamination in the Wilkhan manufacturing pavilions that you see here. So the concept there was that you make a central portico and then suspend wooden profiles from it. So here you can see all the steps of the project. Now, there's an efficiency here because each project has two symmetry axes, and there's 4 of them in total. So there's a 16-fold repetition, which basically allowed them to repeat each geometry mold at least 16 times. So that allowed them to make the complex geometry quite straightforward. But each and every one of these curved beams is different and unique, and therefore challenging to make. But you can see that still, because of the double curved geometry and some very, very simple detailing, simple wooden floor planking, he arrived at this very light, very elegant, very warm finished roof that you see here. Now, to make these curved glue laminated beams is easy if you have one of those very heavy adjustable pneumatic presses, which exist, like this is in Rubner Holzbau, where they have a large curved glue lam beam producer. But if, however, you want to build curved glue lam in a low-tech environment, like, for example, this bridge that was built recently in Malaysia, then you're in a very different construction reality. So for the members of this bridge, they used very labor-intensive, manually controlled steel pressure vises that you see here. And you can imagine that if you want to make a structure where each curved beam is different and unique, that would become inhibitively expensive or labor-intensive. Like, to this day, the factory floor there still has the boreholes in the ground from where those anchors were fixed. So the idea behind Jesu was to see if we can find a way to only use one mold to produce all the beams. And the video is self-explanatory. So we're now looking with our team to push this project forward. Hopefully we'll be able to build it somewhere soon. So yeah, that's it. This is all ongoing work. It's to be continued. There's more available on our website, where also in the publication tab, you'll find most of the recent research papers that we have, as many more videos of fun projects that we have. So to end the talk, the future is already here, just not very evenly distributed. but there's more computing power in your washing machine than NASA used to put a man on the moon. How can you in architecture use these resources to reach a better end result? Thank you very much.
Do we have any questions from the? We had one question from Lakshmi Prasad. If you could unmute yourself, Lakshmi Prasad. Lakshmi Prasad, could you please unmute yourself and ask a question? I'm not able to.
Yeah. Okay. Hello.
Hi, Lakshmi.
Yeah, you're.
Yeah. See, my question to you is the complexity of the design is bringing down the sustainable advantages. It is very interesting, very out of the world creations, especially the one that you have done in Hong Kong, that moon or whatever it is. Making it complicated, using bamboo, making it simple would have been more effective, would have yielded much better sustainability characters than the complexity. But fully appreciating your efforts and your involved design and the innovative design. I just had this ambiguity just like that. I'm just trying to understand. Thank you.
Yes, no, thanks for the question. It's a very, very important one. How to answer it effectively. There's this quote from Miladu Dieste, and the exact words slip me now, but it goes something around like that. Simplicity is a dark god to which we've sacrificed so many things, or rationality or optimization is a dark god to which we've sacrificed so many things. And what's kind of meant with that is the most simple and effective and sustainable way to build. Maybe it's a cube, maybe it's a very simple space. But if everything would be built like that, then we lose something. We lose opportunities to express ourselves, we lose identity, we lose diversity, we lose the joy of inhabiting and occupying spaces. Now, of course, on the other end of the spectrum, if you go fully hyper formal, hyper excessive, and you don't care about any rationality or sustainability, whether that's environmental sustainability, social sustainability, financial sustainability, then of course it's a free-for-all. And unfortunately, in this day and age, with the rate at which global capitalism has been going forward, we have seen a lot of excessive structures where a lot of resources have been wasted in a way that it doesn't per se justify, it's not justified by the end uses that you have. So what I'm trying to do in my work is to still harness and hold on to some of these exciting opportunities that non-standard architectures bring without requiring to go into the high excess or the excessive cost that certain uninformed construction processes may require. For example, the ZCB Bamboo Pavilion, which is a later project that follows after the Golden Moon, there you'll see that, in my opinion, we have an equally engaging and exciting architectural space, but we don't use steel anymore at all, partially because of building regulatory restrictions that we managed to bypass. We could get rid of a steel structure and we arrive at a much more sustainable architectural outcome without sacrificing the excitement of the space that we've generated with that. And so the main argument that I'm trying to bring also to my students here at Hong Kong U is that by analyzing crafts, analyzing materials, material systems, and bringing them in a potentially computational environment where you have potentially greater control of the whole processes, we can think outside of the typical box and still access these more engaging architecture. And that's what I'm interested in. Because if you travel to, say, for example, China, every second and third tier city looks like the same. It's all the same cookie cutter type of architecture that's being put up. And that homogeneity, which is a sacrifice to the god of efficiency and optimization, that homogeneity is also not healthy. So I'm trying to see where we can still find that excitement without going that far. But that's a delicate balance. And yeah, it requires a particular approach and an understanding of tools and materials and techniques to find that opportunity space. I do hope that with projects like Yizo, the last one that I showed you, that's a very luxurious, high standard quality of living type of space. It's a very different user group that I'm targeting than what we were doing in Myanmar. But still, even in those environments, you'll see that the use of wood as a natural resource, which is also a limited resource, can be really optimized without sacrificing the complexity of the space by thinking about how you can put it all on one single mold. So yeah, I hope that answers. Other questions? If you want to, just type them into the chat as well. We can read them from there.
Just hi, Christoph. Very, very nice, wonderful presentation. In fact, you set us very high benchmarks for our schools. Especially in terms of exploring bamboo. In fact, you already showed it in one of your slides, saying that India is again known for very famous for the bamboo, especially in the northeast countries and the states and all that. So we definitely, I think we should explore more the way you have really, because as bamboo is one of the best traditional material and in terms of even the technology. So if we can really explore in these terms, I think we will reach to some certain steps. But very nice presentation, Christoph, and especially just the way you have explored yourself in terms of the final material, the cover of the roof or the fabric you have explored. And also I have seen one of the project like Mountain Retreat, where you have mentioned about the slates. Is it the slates which you have used in that? What is that material? Just wanted to eager to know about that material. The last project which you have explained about, I think
that's just glue lamination. So glue laminated wood, which is a common nowadays a common construction material in the timber industry. So it's an engineered timber wood, and it's a material that originates more in Scandinavia and Austria and Europe, where they have been doing sustainable forestry for centuries. And now with the advent of different adhesives and different glues, which can be sustainable as well, thought it'd be interesting to dab into that area as well. I was quickly looking up while you were talking, because there are some amazing bamboo architects currently operating in India, and I was quickly looking at the INBAR task force, because the name of it escaped me. I think it's Mr. Sanjeev Karpe, who's been doing some fantastic large-scale bamboo constructions from bundled bent bamboo beam assemblages. So there's a great precedent there. There's a lot that we can learn from his work and many other people's work. So I'm always keen to engage in those conversations, because the tools and techniques that I'm developing with my team here are targeted at architects who want to design with these materials, but still require a conversation with local craftsmen and local bamboo specialists, so that the principles can be tailored to the locally available materials, the locally available craftsmanships and the techniques. So it's kind of an open-ended, easily shareable global concept that then requires this local grounding. So it'd be very interesting to see how it could land itself in India. There's a hybrid between raw bamboo and the glue laminated timber structures I was mentioning recently. People have been developing, again spearheaded by INBAR, the International Bamboo and Rattan Organization from Beijing, to work with engineered bamboo, like glue bam, where you take bamboo splits and you glue laminate those. So there's a lot of material innovation that has been taking place in the past 10 years, actually, that are going to create a revolution in sustainable construction.
Thank you. Thank you so much.
Oh, thank you.
Dr. Christoph, we do have some 3 questions. One is from an anonymous attendee.
Yeah.
It says holographic lens does reduce the labor, but would it be cost effective for everyone to use? How much time did it take for the students to get used to the holographic lens?
Okay, no, very, very good question. And I agree, to this day and age, no. But if you look at how quickly smartphones have dropped in cost in only a decade, to the point that they're now pretty much available everywhere in the world. I'm not talking about the iPhone 13, but I'm talking about the iPhone 6 or 7 or some of the older models that have gone through an entire second-hand market as well. Smartphone technology, you can pretty much say, is available pretty much anywhere. And certain predictions have been made that with HoloLenses, a similar evolution is going to be perceived in the next decade. I don't know if that's going to happen. It might. If it would, that would be really fantastic for the type of work that we're doing. So at this point in time, one of these lenses, I'm definitely not going to predict that they're going to be available anywhere on site. But if that technology, once that technology becomes available at a larger scale, to then be ready with the tools that we're working with would be very exciting. I mean, at this point in time, specifically for that reason, we really rely on the resources that are available in certain academic institutes. And just recently now here at Hong Kong U, thanks to a fund that was made available, we've been able to secure a few of them. So with those now, my students are exploring what we can do with them. But the nice thing about the technology is that it's something that you can take in a backpack with you. And with a few battery packs, we can travel to, I don't know, rural India and build something with you. We just take 5 of them with us. And again, we can do something. But unfortunately, at the cost of that technology at this point, keeps it within an academic ivory tower. But different from robotic architecture, for example, where you require, I don't know, $100,000 robot to build something, these HoloLenses are a fraction of the cost of that one. So I do predict that this technology, the HoloLens technology, is going to be much easier to integrate in many rural or low tech or low cost or developing construction contexts, far more than advanced robotic construction, which I think may be restricted to a very narrow market because the cost is so high. So it's a gamble on our end.
Thank you. So there's another question. Says why the cells of your geometry are the same size as the inside. Shubhadra, could you unmute yourself and ask the question yourself?
Hi, Christoph.
Hi, Shweta.
Hey, just I don't know, I was curious. It's more like a comment than a question. Your structures are fabulous and they are very organic. So I kind of tended to compare it to very organic, cellular systems or anything that's organic and made up of different cells. And somehow all these, whether it's a spider web, a shell, or anything that is fractal, ends at a point where all the cells kind of become smaller and self-adjust and then eventually die out. So I was trying to kind of compare it with your geometry and saw that your geometry, when it ended, is actually the same. The cells are the same size as the inside. Just curious as to why you did that.
Which project specifically are you thinking?
I was looking at the dome with the flames.
The Golden Moon, yeah. In the Golden Moon, it's a Fibonacci sequence, which means that it's similar to the seeds inside a sunflower, where indeed there's a large similarity between them, but because of the way they're configured, their number drops. So as you arrive at the poles, the flames reduce in number per meridian, say, but they remain roughly within the same size. And that was strategically chosen by the design team because we knew we were going to be able to rationalize to a certain degree the implementation of it. If I bring the question to a higher level, because you're mentioning fractals and natural systems, I think there's a difficulty in teaching of architecture and teaching the systems of biomimicry in architecture. So biomimicry would be where you look at nature for examples or inspiration to come up with architectural design systems. And the greatest difficulty there is that in nature, geometry is grown, which means that material is expensive, the mass, but geometry itself is cheap because you can easily grow it into any shape that you want to have. Whereas in construction, often it's the opposite. Geometry is expensive and the material is cheap. Like to make a doubly curved brick shell is far more difficult than to grow a doubly curved eggshell, say. So the main drivers are different. So therefore, when you start to look at nature for inspiration, one of the biggest challenges is to identify the principles that are also applicable on an architectural scale. And often those are quite different. So that's why with all the tools that we're developing, we're always bringing it back very quickly to geometry and the materialization of that geometry, the construction details, how you will assemble it, how you will fabricate it, how much wastage is produced along the way, and how you can minimize that, because the principles are very different from nature. Yeah.
All right, that makes sense. Thank you.
All right, thank you for the question. Great question.
We have one last question from Sirupa Dev. What is the fabric material used in the Golden Moon?
For the Golden Moon, it was just Lycra, very simple, very cheap Lycra that we afterwards recycled. Actually, we donated all the material to a local NGO that was working with fabric, so that was very standard fabric. For the, because it was only a temporary pavilion as well, and it was open, so it didn't need to be waterproofed. For the ZCB bamboo pavilion, however, that needed to be a waterproof membrane. So there we have a glass fiber reinforced polymer that we use. So it's basically a tensile fabric that you would see in a circus tent or in a membrane structure anywhere. So it's a common architectural material that in principle is recyclable, but most places don't have the recycling infrastructure to recycle it. So it's again one of those very painful realizations that you think you're working with a recyclable material, and afterwards you realize that people actually don't have the infrastructure to recycle it. So yeah, there's a lot of elements in the supply chain, cradle to cradle, to make it fully work.
Hello.
Yes.
Yeah, actually, it was a fascinating presentation. I really don't know how to thank you enough for that wonderful presentation. The material that you mentioned, that you said that it could be recyclable, but it's not available everywhere. Is it PTFE?
Is it what? Sorry.
PTFE material?
I think so. I don't know it by. I actually have a sample line here. 1 second. I don't know if it says it on it. It could actually be. I'm not 100% sure now. We looked at so many of them. Actually,
okay. Okay.
It's a glass fiber reinforced polymer, so it could be PTFE. I don't know exactly which one it is. It's from a brand called Sergio Ferrari, which is one of the world leaders in large-scale tensile structure, and they have a whole catalog, and we went through quite a few of them before we found the right ones.
Okay.
Ate my mind. Sorry for that.
No problem. I was just curious. That's all.
Ranjin, I have a question.
Yes.
Christoph, that was an amazing presentation. I have a question, although it might sound silly, but still, whether the structural simulation was done for the pavilion, especially for the tripod, that kind of pavilion, and whether structural engineer was involved in it?
There's a great question. There's a short answer and there's a long answer. If we still have time, I'm happy to give the slightly longer answer. So do we still have time?
Yeah. Yes, everybody just wants to hear from you more and more.
Okay, no, I have time. No, so the long, it's really interesting. So in Hong Kong and in most parts of the world, there is no building code for bamboo. But because there's been a bamboo craftsmanship here from long before the British came to set up the building code, they allow bamboo in the construction industry, but it's a gray area in which the bamboo master takes personal responsibility for the bamboo structure, which is a huge risk, especially if you go outside of the typical design solution space. So for that project, we worked with some of the leading engineering firms in the world to help out with the calculations, and we simulated the model ourselves with our low-tech tools, like not real engineering tools, to arrive at the final geometry. We just gave it to the structural engineers and they just came back to us and said, yes, it works, which was a surprise for me. And then later on, which was great because we managed to build the structure, but then later on, when we asked them to sign off on the calculation, the structural engineer refused, because in case something would go bad, he would not have a building code to fall back on which means that he couldn't defend himself in court. So in the end, we had to find a structural engineer, I'm not going to name names, who was brave enough to put his rubber stamp on the calculations and actually get the project built, which is absurd. It shouldn't be like that. But that's how the Hong Kong Building Code is also set up. So you need to really find a brave team to get some stuff going, which is very different than if you would build in Indonesia, for example, or in Vietnam, where it's much more common to take risk and people are more relaxed about it, which is why most of the innovation in bamboo architecture is coming from those parts of the world. But so in the years that followed, my team and I thought that it would be interesting for architects to start to have that knowledge ahead of time. And we started looking into the literature, and we actually found that there's a lack of consensus on how to calculate bamboo structures, because every species has different properties, and within one species, the properties differ dramatically, whether you're working with 3-year-old bamboo or 5-year-old bamboo, if it's wet or humid still, if it's the tip or if it's the bottom. So it's very, very difficult to actually find the right parameters to calculate with. But even then, what we've been able to develop now, and we hope to share those tools soon in the next years, is we've been able to set up a real-time design systems that allow you to predict in real time what the structural performance is of your structures. Because the difficulty is that once you bend your material, you're already using some of the strain properties of the material. And if you bend your structure a lot, it could be that you're very close to the collapse of the material already. But that's a pure geometry problem. So what we've been able to do now is to create this real-time design setup where, as an architect, you design your input, you press play, the system pops into shape, and in real time, it tells you for this species, this diameter, you have this much surplus still to take structural load or wind load. And that's a very, very useful tool, because that has allowed us to predict how large the structures are that we theoretically can make with this. And so that's something we're working on some papers there now in the next couple of months to make that knowledge public. But what was really scary is once we developed these tools, we put in the ZCB Bamboo Pavilion as a test. And the first results that came was that it's impossible with a factor 4, that the structure should not have been able to be built even to begin with. And we checked all the numbers, and it was the conclusion that what we built was not mathematically possible. And then we found out that the material properties that we were working with were from one literature source that the engineers had also worked with, that apparently was incredibly conservative, and that we happened to have been quite lucky having to have a young bamboo species that's still human, therefore is more flexible. Yeah, our structure just managed to be built actually. So we kind of crawled through the eye of a needle there. But that's just to show that some of these projects pioneer and basically plow the way for research to follow up and then produce tools that a larger community can benefit from. And it's really essential that we produce those tools, because otherwise it remains a one-hit wonder that doesn't have the impact that the work in principle could have. And there's a real need for it, because, well, there's so many parts of the world that could really benefit from a more sustainable, engaging architecture. So yeah, that's a long answer. So hopefully in the next couple of months or years, we'll be able to publish some of those tools and share them publicly.
Right. I think we are at the end of our session. Thank you, Dr. Christoph, very much for accepting our request and sharing your time and knowledge to the people sitting on this side of the ocean. You had me at the coffee shop installation. Right. The Golden Moon was also very exciting to watch. And the simplicity of the Bamboo Pavilion was really thrilling to watch you explain the entire process. And I've also noticed that throughout your presentation, you know, you've silently gotten rid of construction drawings. That is quite exciting.
Let me answer that one for a second first. The very first project that we did in Hong Kong here was an interior design. I didn't put it into the presentation because it would become too long. And my greatest frustration was that no matter how many drawings we produced, the people on site were not looking at them anyway. So I thought, if we're going to be working in a low-cost environment, then might as well find a way to get rid of them. and still get to where we need to be.
Yeah, I think the solutions that you had with the hologram and the QR code was absolutely brilliant. I know about these technologies, but to stitch them together, I needed you to explain me that. Right. And throughout the presentation, I really became a student, and you are a wonderful teacher.
Thank you so much. Well, thank you so much for the invite, and thank you so much for the questions as well. It was a pleasure to be with you. Hopefully, COVID permitting, if travel becomes possible again, maybe we can meet in the near future. It would be a joy to meet face to face in the future.
Yes, of course. Me from the BMSSA family, we'll be really excited to have you around.
Okay.
Thank you.
All right,
Thank you
good luck
so
with the
much.
rest of the conference, and hopefully see you soon somewhere, somehow.
Sure. Thank you. Thank you so much.
Thank you, everybody.